Hello everyone and welcome to the first video in our digital logic design course. Before we start studying gates, circuits, processors or hardware systems, I need to begin with the story behind this field. We need to know how did the digital design start and how did we move from simple ideas like logic and reasoning to an era, the era that we live in today, in which we can see tens of thousands of processing cores or even hundreds of billions of transistors on one chip. How did this happen and who started this journey? To answer these questions, we need to go deeper into the history and know more about someone called George Boole. But before talking about George Boole, we need to start from here, a picture that has 5 mathematicians. So we need to understand how these mathematicians think. Mathematicians often look at the world in a special way. What do you mean by a special way? To understand these two words, we need to go back deeper into the history and talk about the apple story with Newton. Newton was sitting next to a tree when he found an apple coming from the sky, an apple coming from the tree. For any of us, we would have eaten the apple and that's it. But for a mathematician, there is something different. Instead of seeing an apple coming from the tree, he see an equation. He thought about it. He said, why the apple is coming from the tree to the earth, not going to the sky? Then he said, this might be because there is something in earth that is attracting the apple. And he was able to describe this by an equation. That is how mathematicians see the world. They try to describe everything by equations. So the world for them is not just a collection of physical objects like the apple. Instead, it is a collection of relationships that can be described with equations. Let's take another example to understand these 2 points. The airplane. When we look at the airplane, we see maybe some metal pieces connected together, some telecommunication components, some furniture also like chairs and so on. We also can see 1 or 2 engines depending on the airplane type. We also see its purpose. We use the airplane to move from one place to another. But when mathematicians or engineers look at the airplane, they see something different. They see some equations. For example, they might see an equation that describes the force that the engine produces. They see another equation that describes the speed. Another one that describes how the air flows through the different parts of the airplane. The most important thing here is that they see another equation that describes the relationships between all of these quantities, because we know that the engine force controls the speed, and also the speed can be affected by the air resistance. So they try to describe this relationship between these quantities by an equation. So we can summarize all of that and say that mathematicians try to describe everything with equations. Then we have a question. Why? Why they use equations to represent everything in our life, including the physical objects? Because if you have an equation, you can do system analysis. You can predict the system behavior. You can know what would happen if we change the input by a specific way. You can also design the system more systematically or design the device more systematically. To understand these points, we need to take another example. A car company. Let's say that we have a car company that needs to design a new car. I want to ask you, what steps they should follow to design the new car? Think about it. The first step is to specify the specifications they need for the new car. For example, they might see we need a car with a speed of 300 miles per hour. We need a car with a maximum fuel consumption of 20 miles per gallon. We need a car with specifications, let's say 8 feet wide or 10 feet wide and 6 feet height and so on. So the first step is to specify the needs, right, for the new car, for the new design. The second step is to start designing. But the question here is how they start the design, how they start designing the new car. Do you think that they immediately build hundreds or thousands of physical prototypes, put them on the road, test them, and finally choose the best one that aligns with the specifications and say, this is the new car? The answer is no. And even if they do this trial and error, there is no guarantee that the best car among 1,000 cars will provide exactly the same specifications. Why? Because they did that without an equation, without a system, without rules. The equation is very important because, in this case, because the equation says if you put this input, for sure you will get this output. If you change the engine horsepower, this is going to affect the speed. If you change the car body in a specific way by a specific design, for sure this is going to affect the fuel consumption. So if you have an equation, they wouldn't need to design 1,000 cars. They might design 1 or 2 cars maximum if they have the equation, or if they have a simulator. And by the way, the simulators are a visual representation of the equations, of the mathematical model, okay? So we can summarize all of that and say they do not immediately build physical prototypes because this is expensive and very slow. They will spend too much money, efforts, and time. So instead, engineers first build a mathematical model using simulators. What do I mean by this? Look at this picture. This is a picture for a car simulator. And as you see, it simulates how the air flows through the different parts of the car. And you can see that the airflow here is different than the airflow across the windshield. And also, it is different than these two cases in the car rear parts. So why this is important? First of all, how they were able to design a simulator that changes the angle of these lines depending on the shape that the air flows through. They were able to do that by equations, right? They cannot describe how the air flow through the different parts without an equation. The equation says if the air flows through a specific shape, let's say a shape like this, then the airflow cannot pass through, cannot move smoothly. It is going to be difficult and the air resistance will be large. But if we design the windshield with this angle, let's say 45 instead of 90 degree, the air can flow smoothly like this. That doesn't mean that the air resistance will be zero in this case, in the 45 degree angle case. There will be an air resistance, but it will be smaller than this 90 degree angle. And this is going to affect the fuel consumption. So the studying or simulating the airflow will give you the rule that explains or that specify the fuel consumption, which is one of the specifications we needed at the beginning, right? So this is how it works, and what the summary of all of that this simulator is based on or built based on the equations, and that explains these 3 points. You can do system analysis as we do here. We are studying how the air flows through the different parts and how this is going to affect the velocity, the speed. This also can affect, I think, the fuel consumption and so on. We can predict its behavior. What do I mean by this? If we change the angle of the windshield from this simulator, we can predict the velocity, we can predict the fuel consumption and so on. We can design it more systematically. Instead of building thousands of cars with different angles and different mirrors, different shapes in the rear, different shapes on front, we can do this by the simulators and only build one physical prototype at the end. That's it, okay? The big question. Here we came to the big question. All of that, these two slides, we can say that mathematicians, about them, we can say that mathematicians try to describe everything around us by equations. And we need equations because of these reasons. But can they describe the human mind? Can they represent the thoughts by equations, the logic, the reasoning, or even the philosophy? This is a very big question. And the first one in history who not only asked, but also answered this question was George Boole. George Boole lived in between 1815 to 1864, and this is his picture. In 1854, he published a book called The Laws of Thought. When you look at the title, you might think that this is something about philosophy, because he's clearly talking about the laws of thought. Maybe the laws here refer to the rules that we should follow to represent our ideas, to write our thoughts, and so on. But this is not how it looks like. If you read the book, you will find something different. You will find that he was trying to answer the big question: can we represent philosophy by equations? So he was saying, can we represent a thought by laws? And laws here refer to symbols, maybe equations, rules, and so on. So before Boole, logic was mostly written in words. Let's take an example to understand how logic statements were represented by words in the past. All humans are mortal. Socrates is human. Therefore, Socrates is mortal. This is a logic statement, right? And as you see, we represented this statement by words. The question here is, can we represent this statement by rules, by equations or not, by algebra or not? So he shifted philosophy, like this statement, to mathematics. His main goal was to turn logic or reasoning, like this statement, into algebra or mathematics. So instead of using algebra to represent numbers like 1, 2, 3, or operations like addition, subtraction, multiplication, division, and so on, Boole used algebra to represent truth values or classes of things. Let's take an example to understand this part here, classes of things. Let's assume that we have two classes. The first class is this one, people who are students, and the second class is people who are engineers. And let's say that we have a logic statement. Let's say these are the classes, okay? These are not groups of people now. But let's say that we have a group of people now, and those people are students and engineers at the same time, okay? So he said, I need to represent this by an equation. So he said, I am going to say x and y. Here he did two steps. The first step is to represent the classes by symbols. He said, I'm going, instead of saying people who are students, this is a statement, I am going to say x. So he represented this class by a symbol called x. And then he said, I'm going to represent the second class by a symbol called y. So we have two symbols here. We need to write the relationship between these two equations. So for example, if we need to add, we might say x plus y, or x minus y, or 1 plus 2, or 2 plus 1. So we have symbols or values, and we should see an operation between these two symbols or these two values. That is what he did. He said, I need an operation here. He looked at the sentence and said, students and engineers, so I'm going to choose this word to represent the whole statement. So the final equation is x and y. Not only that, he mentioned another thing. He said this equation might be equal to false or true. It will be equal to true only if x and y are true, which means the output of this equation will be true if those people in this group are students and are engineers at the same time. Are students means X is true, and they are engineers at the same time, which means Y is true. In this case, this equation will be equal to true. Otherwise, it will be equal to false. So here he did 3 steps, actually, not 2. represented the classes by symbols, represented the main sentence by an operation, and he talked about the output of this equation, and the outputs here are two states, true or false. This is what he invented. And now you might say, we are spending too much time on something very simple. Yes, I told you from the beginning, I'm going to go deeper into the history to understand how did the digital design start. And when we are talking about Boolean algebra or Boolean expressions, you need to understand who's this man, who's Boole, and how he invented the Boole's rules or the Boole's expressions or the Boole's algebra and so on. This is how it started. It started from here. So he said that x and y is true only if both x and y are true. He applied the same principle on the or statement. If we want to say people who are engineers or students at the same or students not at the same time, then we can represent this by saying x or y. And that means people who are students or engineers. He applied the same for the not operation. He said if we say not x, that means people who are not students. This doesn't mean that people who are engineers. Not x refers to people who are not students, because we might have another classes of people. So we cannot say not x is equal to engineers. So this is where the connection between digital design begins in history. So in history, we had Boole saying we have true or false, and we know that the digital system design is based on these two states, true or false. So Boole said that we have two states, and the digital design is based on two states. Boole didn't build computers, he built the language they speak. And this is really important. We have to understand that Boole's work has nothing to do with the digital design at that time, at the time of 1854. He wasn't even trying to talk about the digital design. He didn't know that his work will be used after 70 or 80 years as a breakthrough for the digital design world. Okay, so when I ask you a question and say, do you think that Boole is the father of the digital design? The answer is no, because when he was working on his ideas, he wasn't trying to build computers or digital design. He was trying to answer only one question. Can we represent philosophy by equations? And he was able to answer this question, and he was able to provide the equations that actually achieved that, okay? So for nearly 70 or 80 years, his work was considered pure mathematics with no practical applications, because people at that time was saying what benefits we can get from just representing philosophy by and or not and so on. But as I mentioned, they didn't know that this will be the base for the digital design system in the future. So we can say Boole created a mathematical language for reasoning or for logic, and this is why we talk about logic gates in this course. Do you remember the course title? Our course title here? I mentioned the course title at the beginning of this video. So I said digital logic design course, digital logic design, right? And this is where the word logic came from. The missing step here was to connect this mathematical language, the and, or, not, the true and false, to the real electrical hardware circuits. This step came later with another mathematician called Claude Shannon. Who's Claude Shannon? Claude Shannon is a mathematician lived between 1916 to 2001. This man was working with the relay switching circuits, electromechanical switches. As you see, this is a relay. I don't know if you know the relays and how it works, but let me summarize its operation. It has two parts. A coil that represents the electrical part, a spring and one metal here. I think this metal, I'm not sure yet, because this is an old relay. So the spring and the metal part representing the mechanical part within the relay. So we can say that this is electromechanical switch, or we can say that this is electrical switch. So what happens here with this relay when it works as a switch? It has a metal part like this, so they are open circuit. So if we connect the relay with the resistors, capacitors, and transistors, and so on, I think there were no transistors at that time, okay? So resistor, capacitors, and some other components, the current will not pass until we close the relay like this. So when we connect the coil to a power supply, the current passes through the coil, and the coil generates magnetic field, which generates a force that moves the spring. And when the spring moves, it moves the metal part from one position to another, from this to this, or from this to this. If it moves from here, that means that we turned the relay on, or the switch on, and the current will pass through the circuit that we are designing. And if we disconnect the power from the coil, and by the way, we have a different power to the coil than the power within the circuit that we are designing. So when we disconnect the power from the coil, the switch will be turned off. So the current will not pass through the circuit, and the circuit will be turned off, okay? So that is what he was working on. I told you on, off, on, off. So we have, how many states here do we have? We have 2 states, on, off, right? So here, Shannon said, we have 2 states when we are working on the hardware, right? These 2 states are on or off. And then he realized that someone in the past called George Boole talked about 2 states, true or false, right? So his realization was, he noticed that the on-off state of electrical switches, of the hardware switches like this, mirrored Boole's true or false algebra. You might wonder what is, why we are talking about something simple like this? What is the benefit? Why this is a big breakthrough? It is a big breakthrough because Boole's gave us the rules. And at that time, at 1916 and at the beginning of the 20th century, there were no rules or equations that describe the hardware circuit. So how mathematicians or engineers at that time were designing circuits? They were doing trial and error. Do you remember the car company example? I told you they do not start immediately building physical prototype and then choose the best one. At that time, they were designing the electrical circuits like this. They were trying to connect some pieces together, and if they get the required output, it's okay. If they don't, they try to change the components, try to add more components, try to change how they were connected together, and so on. But with this realization, Shannon said, if we have all the rules that can represent the true or false, even if they are for philosophy, and here in the hardware circuits we have on or off, which we can represent by true or false, but we don't have rules, then why don't we use these rules for these circuits? That is his realization, okay? I hope that you understand this point. So Shannon said, let's try to apply these rules. Let's say that I have 2 switches with a battery and lamp. So they are connected like this, or a bulb. They are connected like this. Battery, switch A, switch B, and lamp. As you see here, we have a battery. This is just a small simulator built on Claude. So battery, switch A, switch B, and a lamp. The lamp will be off if we turn these switches off. Even if you turn one of them on, the battery will not be turned on. It will be turned on only in one case, when we turn these switches, when we turn these 2 switches on. Let's look at how it works. I am hoping that as you see, let's turn the first switch on. The lamp will not be turned on. The lamp will not work. And as you see, this is the first case. Let's take the second case, this one. The lamp is still off. If we turn both on, the lamp will turn on, as you see, and this is the last case. He talked about the same thing for the OR. He said, I'm going to say, if I turn this one on or this one on, the lamp will work as you see here, right? He said, this can be represented by the AND and OR operations that Boole invented. So he said, I am going to represent the first case, this one, by the AND operation, and the second case, this one, by the OR operation. So I am going to say switch A and switch B to represent the first circuit. So the whole circuit will be represented by this rule. And for the second circuit, I'm going to represent this circuit by an equation. I'm going to say switch A or switch B. So this is how it started. This is how we were able to represent the hardware circuits by rules. We used Boole's rules even if he didn't invent them for the hardware circuits, okay? So Boole said logic can be written as algebra. Shannon said electrical circuits can implement that algebra. He proved that Boolean algebra was the perfect tool for designing switching circuits. Before Shannon, engineers could build circuits by the design process was more physical, trial and error. Shannon gave them the mathematical method. What benefits we will get from Shannon's work? As I mentioned, before Shannon, we were designing the electrical circuits by trial and error in most cases. But after Shannon, before designing the circuit, we have the equation. We have AND, OR, NOT, and so on. So before designing the circuit, we write the equations, we put inputs, we calculate the output. If the output as we need, we start the design, the physical design. But if the output is not equal to what we need, we can change the input. We can change the equation itself until we get the required output. Once we have the equation that provides the correct output, we can start the hardware design. That is how Shannon was able to solve the problem of designing the electrical circuits. And that is really important because this man is considered the father of the digital design. This man is the father of the digital design, and you have to know that. If I am working in a university or something, I'm going to put this in the exam. So instead of saying, let's connect switches and see what happens, Shannon said, let's say we have a statement like this. I need a circuit that produces one or turns a lamp on when switch A is true and switch B is false, or when C is true. Let's say someone is asking you to design a circuit and he said this statement. How can you start the hardware design directly without having an equation? You will spend too much time trying to say, I'll design this, I'll put this component here, I'll put this relay here, I'll put this lamp here. This is going to waste time, effort, and money. But instead, we can represent the output like this. A, because we have this on, and B should be false, so not B, and all of this should be ORed with the C, right? So we say OR C. That is how we represent the equation. And then using the digital design, you can design this equation in one step. And this is the main purpose of our course, is to have an equation and then start designing the circuit using this equation. So this is the birth of the digital design. This work provided the mathematical blueprint to design complex circuits systematically rather than by trial and error. And that is why this man is considered the father of the logic design. Then we come to the vacuum tubes era. By the way, I told you that the digital design is based on the two states, true or false. And also now we are using the three operations, and, not, and or, right? So, and, or, not, okay? So all other components that we will use starting then will be switches, because we need two states, on or off. That's why all the components that we are going to use in the digital design are working as a switch. Vacuum tubes, transistors, and so on. So here, vacuum tubes, after Shannon's work, engineers started using his work to build calculators and computers. They have the rules now, so they can design, they can build the equations that provide a specific output. They said, I need some equations that can represent calculators. Once we have the equations, we can start designing the circuits, and also for the computers, not only for calculators. So the first truly powerful computer used the vacuum tubes, and that was in 1945, and it was called ENIAC, and that is the first general purpose electronic computer. General purpose means it can be used for different jobs, for different tasks, not only as a calculator. It had like 17,000 vacuum tubes. It weighed 30 tons, and it took up a whole room. And as you see, this is how it looks like. Do you see the vacuum tubes? We have a ton of wires here, and as you see, we have many engineers are working on maintaining the computer. So the reality is it was fast for its time. It was a big breakthrough, but it was hot because the vacuum tubes are bulbs, and bulbs create or generates heat, right? And this heat needs cooling, and this was very difficult. So it was hot, consumed massive amounts of power. Tubes burned almost every day, so we can say that this is not reliable. Reliable means refers to the stability. We do not have a stable computer. It needs efforts, time. It needs changing almost every day some vacuum tubes and so on. Transistors era. Here I am going fast here because I wanted just to focus on how did the digital design start, and after then starting the transistors, all of this should be studied in the electronic course, not in the digital design course. That's why I am explaining this quickly. So engineers moved from mechanical switching like the relays. Do you remember the mechanical switch that we explained here in this area? So engineers moved from mechanical switching or electromechanical switching to electronic switching. That breakthrough came with the invention of the transistors in 1974, and that is the first transistor. It was designed or manufactured by germanium. I think silicon and germanium are the two things that we use to design transistors. The transistor became one of the most important inventions in history because all digital systems today, including computers, laptops, washers, dryers, displays, and so on, they all based on the digital system design. They all based on transistors. So it can act as a switch, similar to the vacuum tubes, similar to the electromechanical switches and so on, but it is much smaller, and you can look at this and say, oh, it is not small. It has a size similar to the electrical switch. That's because this was the first one. But after that, they worked on the size, and they were able to shrink its size, okay? It is faster because it depends on the electronic movements, so it is faster, not a mechanical movements, right? It is more reliable, and it's more reliable because it is energy efficient, and we don't need to replace transistors many times a day compared to vacuum tubes. So this was the turning point for the digital design. So if Shannon gave engineers the mathematical bridge from logic to hardware, from equations to hardware, the transistors gave them the hardware, the component, the unit that made modern digital systems possible, okay? So in the 1915s, wiring transistors by hand. Let me show you an example. By hand means, if you look at the previous picture, do you see that we have some wires here? And also when they were connecting transistors with capacitors, resistors, and other transistors, they were doing something like that. transistor here, another one here, another resistor here, and they were trying to wire, to put some wires like this wire here or this wire here and so on. So they were using the wires to connect the different components, and that takes too much space. So in 1958, someone called Robert Noyce asked a question. He said, why not put the whole circuit on one piece of silicon? So instead of manufacturing or designing hundreds of transistors, each one on a piece of, on different chip or a piece of silicon, and then we use wires to connect between them, why don't we manufacture one chip that has many transistors or even many components, including resistors and so on? So he was able to do this in 1958, and that is the first integrated circuit in the world, in history. Okay, it had 10 components as far as I remember, and it was called the first unitary circuit. Unitary here refers to the first circuit that includes many things in one unit. Okay, so all components were built into a single block of silicon. Chip size was 3 millimeter by 3 millimeter or 0.12 inches square. 10 individual components. Aluminum lines replacing manual flying wires. Instead of flying wires, there are many aluminum connections, and this is what we call PCB, printed circuit boards today, okay? Something like that, I think, okay? Since then, engineers invented different types of transistors like TTL, CMOS, and so on. In 1971, Intel released the first commercial microprocessor. As you see, this is the first commercial microprocessor. It has a number of C4004, and it had the main components that we use nowadays to design any CPU. For example, they added something called the ALU, the arithmetic and logic unit, and they wouldn't be able to build the ALU without Shannon's work, without having equations, without having something called the truth table. So once they have the truth table, they can get the equations or the Boolean expressions, and they can design the Boolean expressions to design the physical hardware prototype. They have something called registers and control units, and that is what we're going to build in this course. We will try to build by hardware, and I'll show this in videos. The arithmetic and logic unit, the control unit, the registers, and we might build a 4-bit CPU. And in my opinion, this is the main purpose of studying digital logic design. At the end of the course, you should be able to design a CPU. And if you do so, in the next level, when you study computer architecture or computer organization, you will be able to understand the things behind the scene. You will be able to understand what do you mean by performance analysis, performance improvement, because some of these terms will be explained in this course. I don't want to talk about future too much. Let's keep this now for the future. It had like 2,300 transistors at that time. This was big breakthrough also, but nowadays we have hundreds of billions of transistors on one chip, or at least tens of billions of transistors on one chip. Like for example, the B12 GPU from NVIDIA, it has 208,000 billion transistors on its chip. So it is more than 200 billion. Compare this to just 2,000 or something. Since then, also they designed general purpose processor. They designed the embedded systems. General purpose processors, they similar to the CPUs that we have nowadays on our computers, on our PCs, on our laptops, and so on. And they called general purpose because we can use them to execute many functions. For example, we can use our laptops for doing our work in our job, watching videos, listening to songs, maybe using Word, the Word program, the PowerPoint, and so on. So it is a general purpose device. The embedded systems, it is something like that. It is a small microcomputer, and as you see, it is integrated in an electronic circuit. And you can use the embedded system like this one in controlling devices. For example, we can use this one to control the motors within a robot. We can use this one similar to this one in satellites to control to measure and control the temperature and so on. But for satellites, there is something different because we need something that can handle the high radiations in space, okay? The FPGAs, for this, we can write programs to execute something on a specific hardware. We cannot design the CPU hardware on our laptops. But if you want to design a new circuit, a new CPU, you have some specifications and you need we need these specifications to be designed on a physical hardware. You can use the FPGA. So they are hardware programmed, which means we write a program to connect different hardware circuits together, to connect counters, gates, like logic gates, registers, and so on together. So why it is called hardware programmed? Because we write a program to connect hardware circuits or hardware units together. GPUs, this is the breakthrough of the era that we live in today. And if you look at this picture, it was just released a few days ago. This video is recorded on, I'm recording this video on April 26 in 2026, okay? And as you see, a few days ago, NVIDIA released this GPU. I don't remember its name, but it can provide 1.5 exaflops. And the flops here refer to the number of operations per second, not the number of transistors. The number of transistors should be more than this. And this value is 10 to the power of 18. This is insane. This is for the first time in history. This is the first in the first time in history that we can represent a supercomputer on one chip like this one. Okay, so this is how the digital design started, and this is how did we move from Boolean's work, from true and false, to an era in which we can see such chips. That's all for today, and see you in the next one.